Welcome to our exploration of light, one of the most fascinating aspects of physics. Light not only allows us to see the world around us, but it also behaves in intriguing ways when it encounters different surfaces and materials. In this chapter, we'll dive into the concepts of reflection and refraction, uncovering how mirrors and lenses shape the images we see. We'll also explore how these principles are applied in everyday life, from eyeglasses to fiber optics. Let's begin our journey by understanding the fundamental laws that govern the behavior of light. Law of reflection is a basic principle that describes how light bounces off surfaces. According to this law, the angle at which light hits a surface, called the angle of incidence, is always equal to the angle at which it reflects away, known as the angle of reflection. This rule applies to all types of mirrors, whether flat or curved. Understanding this law helps explain why we see our reflection in a mirror and how periscopes and other optical devices work. Let's look closer at how this law shapes our daily experiences with light. Concave mirrors, which curve inward like a spoon, have unique properties when it comes to forming images. When light rays strike a concave mirror, they reflect and converge at a point called the focus. Depending on the position of the object in relation to the mirror, the image formed can be real and inverted or virtual and upright. This property makes concave mirrors useful in devices like telescopes, headlights, and shaving mirrors. Let's explore how these mirrors create different types of images based on object placement. Discussing images formed by mirrors or lenses, it's important to distinguish between real and virtual images. A real image is formed when light rays actually meet at a point, and it can be projected onto a screen. In contrast, a virtual image appears to form behind the mirror or lens, where the light rays only seem to come from, but do not actually meet. Virtual images cannot be projected onto a screen. Understanding this difference helps us grasp how various optical devices function in our daily lives. Refraction is the bending of light as it passes from one medium to another, such as from air into water. This occurs because light travels at different speeds in different materials. When light enters a new medium at an angle, its change in speed causes it to bend. This bending effect is responsible for phenomena like a straw appearing bent in a glass of water. Refraction is a key concept in understanding how lenses work and how our eyes focus light to form images. Refractive index is a measure of how much a material slows down light compared to its speed in a vacuum. It's calculated by dividing the speed of light in a vacuum by the speed of light in the material. Materials with a high refractive index bend light more sharply. This property is crucial in designing lenses and optical instruments. Knowing the refractive index helps scientists and engineers predict how light will behave as it moves through different substances. Lenses are transparent objects, usually made of glass or plastic, that refract light to form images. Convex lenses, which are thicker in the middle, converge light rays to a point, while concave lenses, thinner in the middle, diverge them. The way a lens bends light depends on its shape and the material it's made from. Lenses are used in eyeglasses, cameras, microscopes, and many other devices to focus light and create clear images. Convex and concave lenses have a wide range of applications in our daily lives. Convex lenses are used in magnifying glasses, cameras, and the human eye to focus light and form real images. Concave lenses, on the other hand, are used in devices like peepholes and some types of corrective glasses to spread out light rays and form virtual images. Understanding the uses of these lenses helps us appreciate the technology behind many common optical devices. Human eye is a remarkable optical instrument that uses refraction to focus light onto the retina. The cornea and lens of the eye bend incoming light rays so they converge at a single point, creating a sharp image. If the eye's lens or cornea doesn't bend light correctly, vision problems like nearsightedness or farsightedness can occur. This understanding forms the basis for vision correction using glasses or contact lenses. Total internal reflection occurs when light tries to move from a denser medium to a less dense one at a steep angle, causing all the light to reflect back inside. This phenomenon is used in optical fibers, which transmit data as light signals over long distances without loss. It's also responsible for the sparkling effect in diamonds. Understanding total internal reflection helps explain the efficiency of modern communication technologies. Prism is a transparent object that separates white light into its constituent colors, creating a spectrum. This happens because different colors of light bend by different amounts as they pass through the prism. The result is a beautiful display of colors, similar to a rainbow. Prisms are used in scientific instruments and art to study and display the properties of light. This process is known as dispersion. The focal length of a lens is the distance from the lens to the point where it focuses parallel rays of light. This property determines how strongly the lens converges or diverges light. A shorter focal length means the lens bends light more sharply, while a longer focal length bends it less. Knowing the focal length is essential in designing cameras, microscopes, and eyeglasses to ensure clear images. Spherical mirrors, which are curved, and plane mirrors, which are flat, reflect light in different ways. Spherical mirrors can be either concave or convex, focusing or spreading light rays, while plane mirrors simply reflect light back at the same angle. This difference affects the type and size of images formed. Understanding these distinctions helps us choose the right mirror for tasks like shaving, driving, or decorating. Concave mirrors are widely used in daily life due to their ability to focus light. They are found in telescopes, shaving mirrors, and headlights, where they produce magnified or focused images. Their unique shape allows them to collect and direct light efficiently, making them essential in scientific and practical applications. Understanding their uses helps us appreciate the role of optics in technology. Convex mirrors, which bulge outward, are commonly used as security in rear-view mirrors. They provide a wider field of view than flat mirrors, making them ideal for monitoring large areas or for use in vehicles. Their ability to form smaller, upright images helps drivers see more of the road behind them, enhancing safety. Convex mirrors are a practical application of the principles of reflection. Angle of incidence is the angle between the incoming light ray and the normal, an imaginary line perpendicular to the surface. The angle of reflection is the angle between the reflected ray and the normal. According to the law of reflection, these two angles are always equal. This relationship is fundamental in understanding how mirrors work and is the basis for designing many optical devices. Periscope is an optical device that allows people to see over or around obstacles. It works by using two plane mirrors placed at 45-degree angles to reflect light from one end to the other. This principle is used in submarines and tanks, enabling users to observe their surroundings while remaining hidden. The periscope is a simple yet effective application of the law of reflection. When light passes through different mediums, such as air, water, or glass, its speed and direction change. This change is due to the varying optical densities of the materials. The bending of light, or refraction, is more pronounced when the difference in density is greater. This principle explains why objects look distorted underwater and is essential in understanding how lenses and the human eye function. Snell's law mathematically describes how light bends when it passes from one medium to another. It relates the angle of incidence and the angle of refraction to the refractive indices of the two media. This law is essential for calculating how much light will bend and is widely used in designing lenses and optical instruments. Snell's law is a cornerstone of modern optics. Optical fibers are thin strands of glass or plastic that transmit light signals over long distances. They rely on the principle of total internal reflection to keep the light trapped inside, allowing data to travel quickly and efficiently. Optical fibers are the backbone of modern communication systems, enabling high-speed internet and telephone connections around the world. Lenses can be classified as converging or diverging based on how they bend light. Converging lenses, like convex lenses, bring light rays together to a point, forming real images. Diverging lenses, such as concave lenses, spread light rays apart, forming virtual images. This distinction is crucial in understanding how different lenses are used in optical devices and vision correction. Corrective lenses, such as eyeglasses and contact lenses, help people see clearly by compensating for the eye's inability to focus light properly. They work by adjusting the path of incoming light so that it focuses directly on the retina. Different types of lenses are used to correct nearsightedness, farsightedness, and astigmatism, greatly improving quality of life for millions of people. Plane mirrors are flat mirrors that reflect light to form virtual images that appear to be behind the mirror. They are commonly used in bathrooms, dressing rooms, and vehicles. Plane mirrors provide accurate, undistorted reflections, making them ideal for personal grooming and safety applications. Their simplicity and effectiveness make them a staple in homes and public spaces. Magnifying glasses use convex lenses to enlarge the appearance of small objects. By bringing the object within the focal length of the lens, a large, upright virtual image is formed. This simple tool is widely used in reading, science, and hobbies, demonstrating the practical benefits of lens technology in everyday life. Cameras use convex lenses to focus light onto a photosensitive surface, such as film or a digital sensor. By adjusting the distance between the lens and the sensor, cameras can capture sharp images of objects at various distances. This principle is the foundation of photography, allowing us to record and share moments from our lives. Microscopes use a combination of convex lenses to magnify tiny objects, making them visible to the human eye. The objective lens creates a real enlarged image, which is further magnified by the eyepiece. This technology has revolutionized science, enabling discoveries in biology, medicine, and materials science. Telescopes often use large concave mirrors to gather and focus light from distant objects, such as stars and planets. The mirror collects faint light and brings it to focus, allowing astronomers to observe objects far beyond the reach of the naked eye. This application of concave mirrors has expanded our understanding of the universe. Rear-view mirrors in vehicles often use convex mirrors to provide a wider field of view. This helps drivers see more of the road behind them, reducing blind spots and improving safety. The use of convex mirrors in transportation is a practical example of how optical principles are applied to enhance everyday life. Peepholes and doors use concave lenses to provide a wide-angle view of the area outside. By spreading incoming light rays, these lenses allow residents to see a larger area for security purposes. This simple application demonstrates how lens technology can enhance safety and convenience in our homes. Eyeglasses use specially shaped lenses to correct vision problems by adjusting the way light enters the eye. Convex lenses help with farsightedness, while concave lenses correct nearsightedness. By focusing light properly onto the retina, eyeglasses restore clear vision and improve daily functioning for millions of people. Contact lenses are thin, curved lenses placed directly on the eye's surface to correct vision. They work on the same principles as eyeglasses, but offer greater comfort and a wider field of view. Contact lenses are popular for their convenience and effectiveness in correcting various vision problems. Fiber optic cables use the principle of total internal reflection to transmit light signals over long distances. These cables are the backbone of modern communication networks, enabling high-speed internet, telephone, and television services. The efficiency and reliability of fiber optics have revolutionized the way we share information globally. Rainbows are natural examples of light dispersion, where sunlight is refracted, reflected, and dispersed by water droplets in the atmosphere. Each droplet acts like a tiny prism, separating the light into its component colors. This beautiful phenomenon illustrates the principles of refraction and dispersion in nature. Projectors use lenses to focus and enlarge images onto a screen. By adjusting the distance between the lens and the light source, projectors can display clear, sharp images for presentations, movies, and educational purposes. This technology relies on the principles of refraction and image formation by lenses. Binoculars use a combination of lenses and mirrors to magnify distant objects and provide a three-dimensional view. The arrangement of convex and concave lenses, along with prisms, allows users to see faraway scenes clearly. Binoculars are widely used in sports, nature observation, and navigation. Lasers produce highly focused beams of light by stimulating atoms to emit light at specific wavelengths. Lenses and mirrors are used to control and direct laser beams for applications in medicine, industry, and entertainment. The precise control of light in lasers demonstrates the power of optical technology. Magnification is the process of enlarging the appearance of an object using lenses or mirrors. The amount of magnification depends on the focal length of the lens and the distance from the object. This principle is essential in devices like microscopes, telescopes, and magnifying glasses, allowing us to study details invisible to the naked eye. Virtual reality headsets use lenses to create immersive 3D experiences by projecting images directly into the eyes. The lenses adjust the focus and angle of light, making virtual objects appear real and close. This technology relies on precise optical engineering to deliver realistic and engaging simulations. Safety glasses use specially designed lenses to protect eyes from harmful light, debris, and chemicals. These lenses may be made from tough, shatter-resistant materials and can include coatings to block ultraviolet or laser light. Safety glasses are essential in laboratories, workshops, and construction sites. Solar panels convert sunlight into electricity using photovoltaic cells. Lenses and mirrors can be used to focus sunlight onto these cells, increasing their efficiency. The principles of reflection and refraction are harnessed to capture and direct as much light as possible, making solar energy a practical and sustainable power source. Holography is a technique that uses lasers and the interference of light waves to create three-dimensional images. Special lenses and mirrors are used to record and reconstruct the light patterns, resulting in lifelike holograms. This advanced optical technology is used in security, art, and scientific research. Light sensors detect the presence and intensity of light, enabling automation in various devices. Lenses and filters are often used to focus or select specific wavelengths of light for accurate detection. These sensors are found in smartphones, cameras, and smart home systems, making everyday life more convenient. Traffic mirrors, often convex, are installed at intersections and blind spots to improve visibility and prevent accidents. By providing a wide-angle view, these mirrors help drivers and pedestrians see oncoming traffic, enhancing road safety. Their use demonstrates the practical benefits of optical principles in public safety. Decorative mirrors are used in interior design to enhance the appearance of spaces by reflecting light and creating the illusion of depth. Both plain and curved mirrors can be used to achieve different visual effects. The use of mirrors in design highlights the aesthetic and functional value of optical principles. In this chapter, we've explored the fascinating world of light, reflection, and refraction. We've learned how mirrors and lenses shape the images we see, how the human eye uses these principles to focus light, and how technology harnesses optical phenomena for communication, safety, and entertainment. Understanding these concepts not only deepens our appreciation for the science of light, but also reveals its importance in our daily lives. As we move forward, remember how these principles connect the natural and technological worlds.